Sounds like I can hear the mic, so I think you all can hear it as well. So good afternoon, everybody. I'm Mikko. I come from Silicon Labs. I'm a marketing director, looking after many Bluetooth applications. Me and my team look after applications like electronic shelf labels. There's some Bluetooth technology going on over there, commercial lighting, which is, using Bluetooth mesh as one technology. Enterprise kind of Wi-Fi access point infrastructure, which is adopting IoT as well. So, we have and I tend to think I have a fair amount of experience on the Bluetooth topic. So what I picked up for this year is, as Damon said, Bluetooth mesh, and explaining and going through some of the new features. Not all of them. I spoke last year about all the new features coming up in the latest standard. But a lot of our customers are interested to know, how does it impact my performance? What are the benefits I get? Does it make my life easier? So we run a lot of testing, to answer those questions, and I'm going to share some of that data today. Something going on. All right, there we go. So I'm not going to talk in great detail about the new features in the mesh standard, but essentially, that's just to give you a brief overview. I'll jump to the next slide. Seems like I need to do that. So it's a pretty big standard release. It took, with COVID and with everything, it was like 6 years to develop this standard. So it was a huge effort by many companies, and a big list of new features, complex features. I think what everybody was mainly asking is device firmware upgrade, so DFU. These mesh networks, which typically today are lighting networks, and if you just look up in this room, you see tens of lights. People are deploying occupancy sensors, ambient light level sensors. You have switches, so you can control the light. So these networks tend to be, tens, hundreds of nodes. The device firmware upgrading, networks where you have tens, hundreds, sometimes thousands of nodes. It's a pretty complex procedure, and it's a very mission-critical procedure. If you roll out a firmware upgrade and brick the devices, you need to send somebody on site, and that is expensive. So that's really what a lot of people wanted to have, is a standardized way how to push firmware into those large networks and make it as efficient as possible. Another, probably the number 2 ask we were seeing from the market is something called remote provisioning. So when you go and deploy these networks, you need to set up security, you need to configure devices, you need to define which devices can talk to each other, and the security piece of that with the previous standard happened one by one. So typically the installer had a smartphone application, install the light, set up that light one by one, and it took quite a bit of time. With remote provisioning, we wanted to simplify that, reduce the amount of work and labor that goes to deploying these networks. So now you can actually commission the whole network from a single location. So you can automate it. You can leave your smartphone, if that's the tool you prefer to use, on a table. It sets up the whole network. If you deploy gateways, you can write software on the gateway or even on the cloud that provisions the whole network from a single location. And it saves a lot of labor, saves a lot of cost. So some other features, which I'm not going to talk in detail. There's something called subnet bridging, allows you to break your network into subnets with different security keys. So you can, let's say if you would have a network that covered this whole building, you could break each room into its own network with its own security, and it also limits the traffic to just that portion of the network. And then, additional security features, certificate-based provisioning, especially if you go and deploy these solutions to something like government buildings, there's a little bit more tight security requirements. With the CBB feature, you can use or take advantage of certificates on devices. So when you provision them, you can, know their identity and use certificate-based security, especially when you deploy large networks with a lot of nodes. If you combine the certificate-based provisioning with remote provisioning, you can securely provision the whole network from a single location. simplify it. And a few other features got added as well. So if you're interested in more detail, my presentation from last year discussed all these features in greater detail. But let's move forward. I don't know how many of you are familiar with the two features, so DFU and remote provisioning. So I thought I'll give a quick overview how they work. And, DFU, essentially what it allows you to do, it allows you to see what kind of devices you have in your network. So once you connect to the network, you can query, how many sensors, how many light switches I have, how many luminaires I have in the network, what is the firmware they have installed. So you can see what you got. And then you can check, usually through a cloud, are there any updates available? Once you download an update, and of course every type of device typically has unique firmware. So what runs in the light switch is a different firmware than what runs in the light. Then you select, okay, I have 100 lights in the network. This firmware goes for all the lights. Let's select all those devices to be updated. And then we distribute the firmware. I'm not going to discuss in detail, but there is a broadcast distribution mechanism. So if you pick 20 devices, we actually broadcast the firmware to all those 20 devices to make the transmission as efficient as possible. And once it's all deployed, then you typically send out a single command to all the devices, now update yourself. So that's kind of how it works. And depending on how people build their networks, you can use smartphones as the devices that deploy, do all this. So we have a demo smartphone application that has a demo or a reference how the DFU works. Some people like to build gateways, so you can do that as well. But one thing, especially for the smartphone users, people don't want the installer to be present hours at a time. As you'll see later, this update takes some time. One thing you can do is you can have these dedicated distributor nodes in the network. So you can upload the firmware to one node in the network, which manages the rest. So you can, that upload from the smartphone to the one node in the network is probably 2 minutes, 3 minutes. And then that node in the network can operate for a few hours to distribute the firmware everywhere. So there's that possibility as well. But typically, if people have gateways, they kind of manage it because they're always present. They're always in the network. So that's kind of a high-level overview how this feature works. You'll get the slides. There's a flow chart, how the process works. I'm not going to go in great detail how it works, but, that's available. That's in the specification, so it's easily accessible information. And then let's quickly talk about the other features, so remote provisioning. So as I said in the previous version of the Bluetooth Mesh standard, typically what happened, the provision is a smartphone application. When you add new nodes to the network, you do it one by one. You had to be in the range of that device to do the provisioning. So I could not provision a light which is on the other side of the building from this room. I had to walk over there and pull the app, provision it. Time consuming, expensive. And to simplify that, how it works with the Bluetooth Mesh 1.1 standard, I provision one node to the network. Then I can ask that node, what are the nodes you see in the network? Are they provisioned or not? If I see new unprovisioned nodes, I can use this one node to remotely provision and add a new node to the network. And then I can talk to the second node in the network and say, what do you see? Makes it much more efficient, makes it much more user-friendly, reduces time, reduces cost. All right. So let's then talk about the actual topic, so the performance testing. And to give some background to this, we run a lot of large network device testing at Silicon Labs. And, one test network we have for certain use cases is essentially a small, isolated 7-node network. So we can, these are our development kits, customer accessible. We put them in RF enclosures. We cable everything together. So we use attenuators, RF cables, couplers. And the whole purpose over here is that this node can only talk to that node. This node can talk to these two. So we can isolate every device because typically, if the sensitivity and the transmit power on these devices is such that we get range of tens of meters, and it's really, really hard to build networks where you have 7 hubs. So we just isolate everything so we can have a very controlled and test setup which always remains the same. So we use this the remote provisioning tests where I'm going to share data. It's done with the network like this because we want to characterize the performance and how it builds up as we go further and further into the network. So it uses this setup. For some of the other testing, like multicast performance, reliability, or the OTA testing, we have these large few hundred node networks in multiple of our offices around the world. So what we use for this data collection, we have a 256 node network. We have one in Boston, we have one in Finland, we have one in Budapest. These are typically nodes spread into our offices. You actually kind of see we use those same development kits. They're all Ethernet cabled, USB powered. They're all accessible from a single station, workstation, PC in our network. So, for the OTA testing, where I'm going to share data, we use the 256 node open air network. It's normal office space. There's Wi-Fi, PCs, phones present. So it's a relatively good representation of a situation where these devices would get deployed in reality. So in this testing, we had 256 nodes. They're in 46 clusters. You can see a cluster over here is like 6 nodes, packaged to one. And yeah, they get distributed to various locations in the office. So that's what we use for the OTA performance testing. One quick backgrounder on Bluetooth mesh performance, if you're not a mesh expert, is how Bluetooth mesh works. We use kind of normal Bluetooth 4.0 advertisement for nodes to communicate. So they broadcast information like turn on lights. The advertisement payload in Bluetooth 4.0, it's tiny, and you add all the mesh, PDU on top of it, network IDs. Time to live information, sequence numbers, all the security. The payload you're left with is 1 to 16 octets. And, this is some performance data we have. We typically characterize for every release we do, we characterize, what's our latency per hops. And, we want to keep it as low as possible because the typical spec, like in a lighting application, is when the user presses that, light button, 100 milliseconds, everything needs to work. Lights need to turn on, they need to turn off. If it's 200 milliseconds, 300 milliseconds, the user experience is poor. And what we show over here is how the latency grows as, the further into the network you go. So, typically a one hop, it typically takes in our network 20 to 30 milliseconds per hop. And it consists, there's a little bit of a transmission delay to randomize and try and avoid situations where you have a lot of devices transmitting at the same time, resulting in packet loss. TX and RX takes time. There's 2 levels of encryption, decryption in the Bluetooth mesh stack. So, all that takes time. But typically what we see is one hop is 20 to 30 milliseconds. And it grows pretty linearly the further you go. So a little primer on that, what's kind of the baseline we operate on. So remote provisioning, again, as a reminder, this is done with the 7-hop RF isolated network, so we have a very controlled environment. How this test runs, we have a PC that starts the provisioning, essentially provisions the first node into the network, and then, it starts a relay functionality on the first node, and then it starts to, it basically queries the first node, what other nodes do you see? And that first node will only see the second node in the RF box, and then we provision that and move on and on and on and on. And the provisioning, there's a lot of security set up, but there's tens of messages that get exchanged between the provisioner and the node to be added. It takes time. So you kind of see when you add the first node to the network, it's, we run this test a few hundred times, average the value is about 2 seconds to add the first node. When we go to the second node, we already go over one hop, which does add 20 to 30 milliseconds of latency one way for every message we send. So naturally, that grows over time. So we see 2.5 seconds, 3.5 seconds, 4 seconds, and so on and so on. So pretty, predictable behavior how it works. But again, if you would start to think that, there's an installer walking around with a smartphone searching for, what's the next node I need to go and add, select that node, provision it to the network, that takes 30 seconds, 60 seconds per node easily, even more, the further you need to walk. So essentially, this kind of roughly we say, with single hop provisioning, it takes about 2 seconds to add nodes to the network. Of course, the further you go, that latency goes up because there are more hops. But again, bottom line is, even with this performance, this is significantly faster than doing it manually by the user. And you can automate it in software. You can avoid human errors, issues, training people, and all other things. So, significantly should simplify and reduce the cost of deploying these networks. All right, moving on, DFU performance measurements. Again, a reminder, we do the TIS testing in the 256 node open air network, so to speak. For these results, we actually updated only 60 nodes in the network, not all of them. And the firmware is distributed, so the whole process runs on a PC, so that it discovers the nodes, selects the nodes to be updated, distributes the firmware, and does all of that. And a little bit of a process description, maybe not necessary for me to go through that. Then these are vendor specific. We selected something called a Bluetooth Mesh Light Controller. That's typically the software that runs in the luminaire. It can take sensor inputs from occupancy sensors, ambient light level sensors, switches, and then, that firmware is responsible of turning on the lights, turning them off, dimming, whatever you do. So that's typically the most complex node in the network. So hence, it means the firmware is the largest. So, and we have capabilities to compress the firmware. So we did 3 scenarios, a fully uncompressed firmware. It's about 350 kilobytes in size. We can run 2 different compression algorithms today, which are supported by our bootloader. So we can run LC4 compression. It only compresses around 10%, but it's a very lightweight compression, doesn't add a lot of code size. We can do a little bit more better compression with LCMA that can cut down to 30% out of the firmware size. So a lot of with the slow firmware updates like this, the point I'm trying to say, it kind of makes sense to compress the firmware. You save a lot of time, energy if that's meaningful, pushing out the firmware. So in this current testing, you can see that these updates are not super fast. So pushing 350 kilobytes to 60 nodes took a little over 3 hours. The key point over here is the network is still operational. So the lights are active. You can turn them on, you can turn them off. They operate, but in the background, the firmware is constantly getting uploaded. And once the upload is complete and we verified that every firmware is intact, no CRC errors, everything got transmitted, then you initiate the update process, which is probably 10 seconds. And you can see the impact of compression, easy guess. The more you compress, the more time you save. But it's even with LCMA and getting about 100 kilobytes out of the firmware size, it's still, a little over 2 hours, almost 2.5 hours to upload. So it's not a fast process. If you've used the scenario where you update the firmware on your headphones, that's a point-to-point upgrade. We get that 1.6 megabits at best, and the updates are in the matter of seconds. But this runs in the background. The gateway can do it. One of the nodes in the network can do it. So it doesn't necessarily mean that the user needs to be there for 2 hours and wait for the progress bar to slowly go up. So again, kind of key points. It's multiple hours to update. Network is operational while this is happening. It's a background upload. If you start to calculate what's the update time per node, because it's a broadcast update. As long as you have the same firmware going out, it is actually pretty reasonable, so you can get down to a few minutes per node. So that's a pretty reasonable time, similar to a point-to-point upgrade from a phone. And again, last point, no-brainer, compressing the firmware makes a lot of sense if you want to optimize the time. And that's it. I know it's a lot of information coming in very quickly. We have a lot of performance testing data on our website, covering multicast scenarios, other types of use cases, a lot of more information there. I think I had some links. Yes, there's one link. We do have a 10-15 page document characterizing how the Bluetooth Mesh 1.1 standard performs as we've tested today. So a lot more information available, and you can always contact our folks at Silicon Labs, and we're happy to share this data. Not just for Bluetooth, we do this for Zigbee, we do this for Matter, we do this for Bison, a lot of other mesh networking technologies. So we have a fair amount of knowledge on how to test large networks, and I think my colleague Petter will talk about another type of scenario where we scale this to 1,000 or more devices. Any questions?